Good evening, everyone. My name is Aryan, and I'm back with another video. And in this video, I want to discuss about the fundamental forces of nature. You see, we interact with large number of forces. We carry weights, and in our daily lives, we interact with large number of forces. Okay, and if you ask someone naively that what are the total number of forces, the people may naively say that probably there are 10, 20 and even 30 forces. But what if I tell you that fundamentally physics has identified only 4 kind of forces, okay, and the ones that we interact with are probably 1 and not more than 2, okay, because the rest of the forces exist inside the nucleus and 1 even inside the proton. So we interact with only 1 or 2 kind of forces, but in general physicists have identified that there are 4 fundamental forces of nature, and we are going to discuss about them. So you have the 4 fundamental forces nature. First is the gravitational force, second is the electromagnetic, third is the nuclear, and fourth is the weak force. Gravitational force of attraction is the weakest among all. Okay, strongest is the nuclear force, followed by the weak force, then the electromagnetic force, and then the gravitational force of attraction, which is the weakest among all. Let's first discuss about the gravitational force of attraction. It's a long range force. Now what is the meaning of the long range force? The gravitational force of attraction, as you might have studied in your lower grades, that the gravitational force of attraction is the force by the virtue of its mass. Okay, if you look at the expression of gravitational force, it is capital G, which is a constant. It's a very, very small number. M1, M2 are the masses and R is the distance. Okay, so the meaning that it's a long range force means that even if you increase the distance to a very, very large number, okay, still the gravitational force the gravitational force of attraction between those two bodies will exist on papers. Okay, this force is not gonna vanish abruptly. Okay, if you look at this expression, the force varies as 1 by r square. Okay, so the force, if you plot its graph, the force does not have a kink anywhere. Okay, this force decreases as 1 by r square, and even at distance infinity. Okay, even if you put very, very large numbers, you plug in very, very large number instead of this r, the force, though it would be very, very small, it would still be some finite value. Okay, so this is meaning that it's a long range force. Okay, it even exists between the particles at a very, very large distance. Okay, now what happens? This M1 and M2 are the masses of 2 objects. What happens if I put this M1 as the mass of Earth and this small r as the radius of the Earth? That is, I am considering one body to be the Earth and second body probably the objects that are on Earth. In this situation, this gravitational force of attraction is called as gravity. Okay, so if I substitute this F is equal to capital G, capital M, where this capital M is the mass of Earth and this r is basically the distance between the center of the Earth to that object. Okay, this r, so in that particular case we call this gravitational force of attraction as gravity. Okay, and this capital G M by r square, this is a constant. If you see, because mass of the Earth is a constant, the distance between the center of the Earth to any object which is on the surface of the Earth, or even for some for a simplification of some calculations closer to the surface of the Earth, we can still probably assume that distance to be the radius of the Earth itself, and in this situation this particular term is a constant and we call this force as mg. This capital G M over r square, we are calling it as g, and this g is basically called as the acceleration due to gravity. Okay, this acceleration due to gravity is 10 meters per second square. Okay, this acceleration due to gravity is the acceleration by which the objects which are closer to the surface of the Earth, they fall towards the center of the Earth, and it is same irrespective of whatever mass you are choosing. Okay, because you can see there is no dependence of mass on the acceleration due to gravity. There is no dependence. This m is the mass of the Earth, not the mass of the object. Okay, so it is irrespective of the fact that what is the mass of the object. You know, all the objects, they will, basically they will fall towards the center of the earth with the same acceleration, which is called as the acceleration due to gravity, and its value is 10 meters per second square. Okay, this is the first kind of force. Now let's come to the second kind of force. The second kind of force is the electromagnetic force. Like the gravitational force of attraction is the force by the virtue of its mass, the electromagnetic force of attraction or the repulsion also is the force which exists between the two charges. Okay, this is the force by the virtue of the charge. If there is no charge, then there is no electromagnetic force. Okay, so this is the force which acts between the two charges. Okay, and it can be repulsive as well as attractive. Okay, it's also a long range force. It means that even if you separate the two charges to a very, very large distance, on papers, on calculation, the force is theoretically, it is never zero. Okay, this force theoretically is never zero. It can be a very, very small number, but it's a finite number. It is never zero. It is zero only at r is equal to infinity. Okay, but you know, infinity is not a number. Okay, so the expression for this force is capital K, Q1 Q2 over r square. As you might have understood by now, this Q1 is the charge on first object, or you know, the first body. The Q2 is the charge, the second charge, and this r is the distance between the two charges. Not like the gravitational force of attraction, this capital K is a very, very large number. Okay, this constant is 10 raised to the power 9. You know, not like the gravitational force of attraction, where this constant is a very, very small number, thereby making this force of attraction between the two objects very, very small. Okay, and this is the force, of course, this is the force due to which the electrons revolve around the nucleus. You know that nucleus is positively charged. It has protons and it has neutrons, making the nucleus positively charged. And we have electrons that are revolving around the nucleus. So basically, due to this, this positive, basically sort of this attraction provides the centripetal force to the electron so that it can revolve around the nucleus. This is the theory which was given by the Bohrs. Okay, Niels Bohr. And you can see that this particular thing, that this is a very, very famous example, as you might have guessed by now. This is a book which is kept on a table. Okay, and we say that we ask this particular question. Okay, we understand that the book has this mass and the book is pushing this table in the downwards direction by the virtue of its mass. But you know, basically, why is the table pushing the book upwards and not why? We understand that this is by the this is due to the Newton's third law. But you know, how is basically the table pushing this book upwards? You know, so the answer to this question is that, you know, the atoms that are present on the surface of the book, okay, in the downward side, and this table, okay, the surface of the table, which is basically eclipsed by this book, you know, the backside of the book, you know, the atoms that are present on the surface, you know, they interact, okay, and the resultant force is the force that we see is due to by the table onto this book. Okay, so there are, so you know, in general you might say that Aryan, why is this so? Because you see, the atoms that are present on the surface of the book, they are neutral, yes, and the atoms that are present on the table, on the surface of the table, they are also neutral. But why are they so? Basically, you are wrong. So why are they basically interacting with each other, or how they are interacting with each other? I'll give you an example. You see, if you consider one dipole, okay, so one dipole means that you have a positive charge and a negative charge, and you have another dipole. So in general, if you consider one dipole, so effectively the charges are zero. Yes, you have the positive charge and the negative charge, they are zero. You consider another dipole, you have two dipoles, there also, you know, positive, negative, it's zero. But what happens when you bring those dipoles closer to each other? Yes, they do exert force on each other. Okay, so when the atoms that are present on this book, on the surface of this book, and the atoms that are present on the surface of the table, when the book is very far apart from each other, when they are very far from each other, okay, there is no way that there is going to be any electromagnetic interaction. But when the book is kept on the table, the atoms that are present on both the surfaces, they are very, very close to each other. So yes, in this particular situation, there is a net electromagnetic there are electromagnetic interactions between the two surfaces, and therefore you have a resultant force which is exerted by the table onto this book. Okay, similarly we have another example of a handshake. So you can see that when the two people are shaking hands with each other, you know, the atoms that are present on the surfaces of the two hands, they are very, very close to each other, and therefore the atoms interact with each other. And you know, even though the atoms individually they are neutral atoms, but like I gave the example for dipole, even the dipole, the net charge is neutral, but when the two dipoles, they are very, very close to each other, so they exert forces on each other. Okay, and the handshake, when the two people shake hands with each other, so there is this electromagnetic forces of interaction because the surfaces have atoms. Okay, this is the second kind of force. Now what is the third kind of force? The third kind of force, you have the nuclear force. Now first thing is that it's a short range force. Why I am saying that it's a short range force? Because this force exists not inside the atom. This force exists even deeper. This force exists inside the nucleus. Okay, so this force acts between two protons. Okay, this force can act between a proton and a neutron, and this force can also act between the neutron and the neutron. So what does this tell us? That this force is charge independent. Okay, it also acts between the proton and proton, it acts between the neutron and neutron, and it acts between the proton and the neutron. Okay, this is the force which keeps the nucleus intact. Now why I am saying this? You see, you might have whenever you might have studied about atoms and all that stuff, you know, there would always be one question in your mind. You know that Aryan, that you have a nucleus. Okay, inside the nucleus, the neutrons do not exert force on each other. There are no basically neutrons are neutral, right? And protons have positive charge on them. And you know that two protons, and there are large number of protons inside the nucleus. So the protons and protons, they repel each other, right? Due to this electromagnetic force of interaction. And the neutrons basically do not exert any force on each other. So why doesn't the nucleus, basically just fly apart? You know, why even is the nucleus intact? Because the protons repel each other. There are no forces which exist between the neutrons. So why doesn't the nucleus fly apart due to the repulsion of the protons? The answer is very simple. This means that there has to be some another kind of force which exists between the nucleus, and that force is called as the nuclear force. This is the force due to which the nucleus remains intact. And you know, we can draw another conclusion from the facts that I mentioned above. You know, the nucleus does not fly apart means that this nuclear force has to be stronger than this electromagnetic repulsion of the two protons. And indeed it is so. The first point says that it's a short range force. Okay, it's a short range force means that this force exists in the range of 10 to the power minus 15 meters, which we call as the femtometer. Okay, you can see here, I have also drawn a graph. You can see that this part shows the attractive part, okay, and this part shows the repulsion part. If you look at the diagram carefully, this is basically the typical region of the nucleus, okay, between 1 to 3 femtometers, okay, and this dotted blue line shows the Coulombic repulsion force which I was talking about between the two protons. This is the Coulombic repulsion force, the dotted line, and this you can see the red line. Okay, this is in the attractive region. If you might see, this is very, very stronger as compared to the Coulombic repulsion, as it is evident from the graph itself. Okay, but you see that this force dies down as you approach 3 femtometers or 4 femtometers. Okay, so it's a very short range force. It exists in the order of few femtometers, 2 femtometers or 3 femtometers. After 3 femtometers, you can see the force dies down, and there is still and this Coulombic force is a long range force. Okay, but you can see between the two protons there is also another force, which is the nuclear force, which keeps the nucleus intact. It's a very short range force. It dies down after 3 or 4 femtometers, but it is very stronger, approximately 50-60 times stronger than the Coulombic repulsion, and this is the force which keeps the nucleus intact. Okay, it says that it is the force between nucleons. Nucleons means the protons and the neutrons, and combined they are called the nucleons. So this also acts between the two neutrons, it acts between a neutron and a proton, and it also acts between the two protons. Okay, but of course when the two protons are separated to a very large distance, then this nuclear force does not come to the picture, because as I have just told you that it's a very short range force. So this nuclear force only comes to the picture when the two nucleons are very close to each other. Okay, now the last kind of force that I'm going to discuss is the weak force. Now this force is even, the domain of this force is even inside the proton. The nuclear force that I told you, it exists inside the nucleus, but this weak force exists even inside the proton and the neutron. So what basically happens? So basically, what is the origin of this weak force? What happens that, in our nature, whenever the nuclei are formed, okay, in some reactions or, naturally occurring reactions, you might have studied about the NZ graph, okay, in the nuclear physics. In the NZ graph, there are some of the nuclei, in which the number of protons are very larger than the number of neutrons, and even, in some cases the number of neutrons are very larger than the number of protons, thereby making the nuclei unstable. Our nature, or the objects in the nature, they always tend to attain stability. Okay, and this is not very stable, that inside the nucleus you have very large number of protons as compared to neutrons, or vice versa. So what happens that in this weak force, if you have a nucleus, a naturally occurring nucleus in which you have large number of protons, for example, the large number of protons as compared to the large number of neutrons, we can have the situation otherwise also. Okay, in this situation, what happens? A proton usually gets converted into the neutron, thereby releasing a positron and a neutrino. Okay, it's also a very short range force. This force exists inside the proton, but you should not confuse that a proton is made up of a neutron and an electron and an antineutrino. No, this basically just gets converted into the neutron, thereby reducing the number of protons and increasing the number of neutrons, so that we can attain stability. We can have a reaction otherwise also. Okay, say you have a nuclei in which the number of neutrons are larger than the number of protons. In that situation, a neutron can get converted to a proton, thereby releasing an electron and an antineutrino. Okay, so it's a weak force. Okay, but this weak force don't go by its name. This weak force is stronger than the electromagnetic force and the gravitational force. This gravitational force is the weakest of all the forces. Okay, so this is what I wanted to talk about in this video. If you guys have any feedback, you want to discuss about something, you can always comment it down in the comment section. Thank you.